In mathematics, there are many concepts that may seem alike at first but have distinct meanings and application. Some ideas complement each other while others stand in contrast, shaping the way we understand mathematical structures and reasoning. In this video, we will explore some of these fundamental concepts, uncovering their differences and connections to build a clearer perspective. My name is Shaunak and you're watching this video on my channel Physics for Students. Well, first what we will look is this one, equation and identity. First, let us understand what is an equation. If I go by a very simple definition, then the equation is basically nothing but a mathematical statement that shows the equality of two expressions. But remember, it is only and only true for specific values of the variables. We have started reading equation right from our childhood, but I want to give you a different perspective between these two concepts. Now, if I take this kind of equation, x squared minus 4 equals to 0, what it comes out is that this equation is true and only true when x is equal plus minus 2. That means it should be equal to plus 2 or minus 2. Then only whatever is the statement that it should be equal to 0 will become true. But also what is important is that it will become false for any value of x. Now, when we state that x is equal to plus or minus 2, that means we say that this is what is called the solution of the equation. We heard it in numerous advanced mathematics: solution of Einstein field equation, solution of Gauss's law of gravity. So the basic central idea is this. So if we take x equals to plus 2, then the statement becomes true because the left hand side equals to left hand side and it shows 0. And even if we take x equals to minus 2, hence the statement stands to be true. And also what we get is that the solution of an equation is the set of all those values when they are substituted in the equation makes the equation true. So this is what is called the solution for equation. We also see there is an equal to sign, and this actually means that it holds true only for certain values of the variables involved. That means it is not true for all the values. This is what we call is an equation. When we come to identity, we get the definition something like this. There are expressions, it is also an expression, are always equal to each other regardless of the values that are of the variable that contain. Now, in case of a mathematical identity, we write something like this one, which looks like a kind of an equal sign which has got an extra line with it. So we can say that an identity is basically a special type of equation which is always true for all values of the variable within its domain. Now, in equation we told that it is basically true for specific values. Here we also tell within its domain. So let us see some of the examples of mathematical identities. For example, 2x plus 4x equal to 6x, 2a squared plus 3a squared equal to 5a squared, and so on and so forth. So these are examples of mathematical identities. Typically we see this one, very simple, a plus b whole squared equal to a squared plus 2ab plus d squared, and this holds true for all the values of a and b. Now here is a catch, that when I stated the definition, I underlined it, is that within its domain. So what do we mean by within its domain? We mean that an identity is only and only valid within the set of values where both sides are very much well defined. We will see some examples and things will become clear. Now there is something which is called an algebraic identity, which is we have already seen. So the domain, as we were talking, are all real numbers because addition, multiplication and squaring are always defined. And this is also true for complex number. Trigonometric identity, for example, sine squared x plus cos squared x equals to 1, but it is not equals to, it is, I would say, with that special sign, which is an identity. This is domain for all real numbers, or since sine and cosine are defined for all x as well as complex values. Now, in case of a logarithmic identity, log AB, which is the identity of log A plus log B, this is true for real number, but not valid or for negative or complex number, because in that case we have to extend the logarithmic using the complex logarithm, which I have not shown. So this is true only for real number, not for complex numbers. Fractional identity, this one 1 upon x times x is identical to 1. This is again true, but not always true for x equals to 0. All real numbers except x equal to 0, because division by 0 is undefined. And here, as you can see, that because division by 0 is undefined. So what we can say is that when we say an identity is true for all values within its domain, we mean that it holds for all values where the mathematical operations are valid. We talked about that, the addition, multiplication, squaring, etc. So this is what is called, basically these are the examples of identity. Now the question arises that are they the same? I mean to say equation and identity, they are the same? Certainly not. Certainly not, because an equation only holds true for certain values of variables, whereas an identity holds true for all values of a variable in its domain. And remember that every identity is an equation, but not every equation is an identity, obviously, because the identity is a superset, equation is one part. So from here what we can say that any identity is definitely an equation, but is a special type of equation. So equations can be transformed into identities under special conditions, which we will see in the next part of our video. Now the next part, which is very, very important, is that let us consider this kind of an equation. Now how can we identify that whether it is an identity or not? So this is not an identity because it is not valid for something which calls x equals to 2. But how can we validate it? Can we validate it? Definitely we can do. So the first step is that we need to identify that why it is not an identity. So given this equation, what we do is that we factor the numerator, that is x squared minus 4, and we write something like this. Then what we do is that we cancel the common factor. So for x not equals to 2, we cancel x equals to 2, which leaves something like this. But when we substitute x equals to 2, at x equals to 2, the original equation becomes this. And here is the problem, that this is something which is called undefined. So hence the expression does not have a valid value for x equals to 2. So this is a kind of a check, but there are other numerous checks where you can check in whether an expression or an equation is an identity or not. Here we have seen this is not an identity because there is a factor of undefined value 0 upon 0, which is undefined, hence it is not valid for x equals to 2. Now the question comes that can we turn it into an identity? That means can we turn this equation into an identity? Definitely we can do that. How? Let us look in this part of the video. Now the first thing is that we need to restrict the domain and include x equals to 2, because the basic definition of identity, if you follow right from the beginning of the video, is that some expressions are true, are always equals to true, but identity is true within its domain. So the most important thing here we need to do is that we need to specify the domain. And this equation holds for all values of x. So adding the condition for x not equals to 2, this equation effectively becomes an identity within its domain. But the question is that can we verify this? Definitely we can. So we need to substitute some value which is not equals to 2. So for example, how to verify this? So if we substitute x equals to 1 over here, we get a value 3, that is the left hand side, and the same value 3 on the right hand side. So it is an identity because both of these turns to be true. Again, if we substitute equals to 2, then the left hand side and right hand side becomes equals to 5, and hence we call it as an identity. So this is how we can check an equation that whether it is identity or not. So here comes in a tabular structure, what are the features of equation and identity? Definitely the definition goes first. This is valued for specific values of variables, and this is a mathematical statement which is valued for all values of variables. The symbol is equal to, and this is something different. The validity is for some values, but it is true for all values. For example, this one is only valued for x plus minus equals to 3. and it is identical 1 when true for only value x. So this is the relation, but the next question is very important. How do we identify an equation and an identity? That means how will we come to know whether this expression is an equation or an identity? Now here you can see that the first criteria, we will take this as an equation, this as an identity. Is it true for all values of x in its domain? Yes, definitely, as we see 0, 1, 2 and so on. And this is no, because x plus minus equals to 2. Second point is that, is it valid for only specific values of x? Definitely not, because this is true only for x, and this is true for x plus minus equals to 2. Can this be simplified? Okay, so let us see an example. So this, as you can see, equals to 1, and this is 0 and minus 3. So one part is yes and some part is no. The second one is that does it represents a fundamental algebraic truth? Yes, definitely it does. For example, we will see the example, and it is no. This is absolutely no. Can this be transformed in another form? Yes, as we have seen with this famous algebraic expression x a plus b whole square, and this is yes, because this can also be done. And are there cancelling common factors? Do they create any kind of a restriction or not? Yes, they do, if the domain restricts, and yes, because we have seen that division by 0 creates some problems. So from here we can draw a conclusion that identity is a subset of equations. I've used the subset symbol, but remember the reverse is not true. That means equations are not subsets of identity. Now in case of reading this very basic fundamental of equation and identity, you will see that we come across this kind of a sign, this kind of a sign, and sometimes the same identity is also written with an equal to. Okay, now my question to all of you who are watching this video is that why it is so? Is it that it is something obsolete, we don't use the topmost signal, or does it create a confusion, or for the case of simplicity we are using the equation sign? Let me know in the comment box if you really know and you feel that this is something important for our knowledge to remember that what is basically and why it is the difference. We turn our attention next to something which is very important, which is called a null set, empty set. Now I won't say that whether they are the same or they have the difference, but things will come clear once we go ahead. Now first of all, let us understand what is a null set. Obviously it is very clear, a set that does not have any values, and it is denoted by this curly braces. So you can see here there are no elements, so absolutely there are no values. Okay, we can take a very weird example, for example a book which has got no sensory organs like ears to hear or eyes to see. So the book do not have any sensory organ, we call it as a null set. A null set is also denoted by this sign or this sign or this sign. Now the last one is a phi, and I won't recommend you to write really a phi to denote a null set, because mathematically this is absolutely not true. So null set is basically a circle with a kind of a diagonal line and the curly braces, either this or that, that is one. Now the question arises, we understand a set which has got no element, this is called a null set, for example things like this, but the question is that why do we need a null set? Let us understand this. Now say for example we have a set which carries these values 1, 3, 5, 7, and we have another set which is called B, which has got these values 2, 4, 6 and 8. You can think of apples or oranges or anything. Now suppose we are given the rule of intersection. So what is the rule of intersection? Is that we are going to compare all the elements of set A with all the elements of set B, and any elements that exist in both A and B we need to write inside the set with the intersection sign. And here you can see 1, 3, 5, 7, 2, 4, 6, 8. It doesn't contain any of these values. Hence we write this intersection equals to either the curly braces or the circle with a diagonal line, which is basically called a null set. So we did an example, very simple intersection not containing any values, which is common to both A and B. We call it as a null set. Now let us take an example, A equals to 1, 2 and 3. Now the question comes that can we say a null set, that means it contains nothing, it is absolutely void, right, is a subset of A. And what is A? A contains certain values, right? So can we say that null set is a subset of A, which is written like this? Phi or this sign is a subset of A. Definitely. Definitely we can say that null set is a subset of A. Now this creates a confusion. Let us understand why. Now first of all, I will give you two examples. Number one is this one. What does an empty set contain? The curly braces. It contains absolutely nothing. Now what does this A set contain? The one with values. So it actually contains 1, 2, 3 and nothing. Okay, so what we can say is that because every set has nothing apart from the other elements, we say it as null set is a subset of every set, and we write nothing is a subset of A, and here we write this one is a null set is a subset of A. And also remember, because nothing is a part of this set, we said that nothing is actually a part of the subset of this is a subset of the main set A. And also remember that the null set is also a subset of itself. That means nothing is a subset of nothing, and since both sets actually have nothing. Okay, let me give you a little bit easier example, not in terms of mathematics, pictorial description which will make things easier. Now consider this to be a basket, right? It has got absolutely nothing. So what is it? It's a null set. So if you take nothing, that is an empty basket, then everything inside it, that means the nothingness, is already in another basket, isn't it? So any empty basket, for example 1, 2, 3, these baskets are always a part of the big basket. Okay, so that is why we say this nothingness of the empty basket, this nothingness of the empty basket, and this nothingness of the basket are actually containing in all those small baskets. So hence we say that an empty set or empty basket is always a part of another basket. So we say that empty set is a subset of 1, 2 and 3. What is also important is this one. So for example, we draw this basket, right? We have got this basket and there are certain elements 1, 2, 3. It can be anything. It can be anything. And let us say that there is also another basket and this is empty. So what is this empty basket? This empty basket is still a collection, isn't it? It is still a connection, but it is a collection of what? It has got no objects. So what we can say from here, that you still have the box or you still have the basket, but there is nothing inside it. So it is definitely a collection, but it is a collection of no objects. Now let us consider this sign. What is this all about? A set, an empty set which has got another empty set. A set containing the empty set. Let us imagine in this way. Let us consider this basket, which is the big one, the big basket. Inside the box there is an empty box. So the big basket is also empty, and within that there is another basket which is also empty, isn't it? So that the set does not have an element in it, has got another set inside of it, and this element has itself the set, that is the empty set. And that is why, if I go back, let me go back to the previous few seconds of this slide. Here you can see, okay, let me further go back. Now here you can see, here it is, null set is a subset of null set itself. Now in order to demonstrate that, I have used this analogy. If null set is a subset of the null set itself, that means inside the empty box there is another empty box, and the set does not have any element in it, and another set is inside it, and this inside element of that set is also empty. So you can imagine it this way, depending upon the levels. For example, the curly braces, you can imagine this to be that big basket, the one, the black dotted one. And when you say the phi inside it, or I should not say phi, that the null set, this is actually this one, that is the brown one which has got it. So this is the thing. So first of all, remember that a set which has got null or empty, it is also a collection of no objects, and inside the empty set there is another empty set which is also null, and that is why what we say that null set is a subset of null set itself. Now what about this? As I talked earlier, that null set, is it a subset of any set? For example, in this case 1, 2, 3. So here it is. Everything that is inside the empty set is also inside this set, which has got elements 1, 2 and 3. Right? So that is why we said null set or empty set is a subset of this set. And every element of the empty set is also inside this set. For example, A, B or C. So every element of the empty set, that means the vacant one, is also inside this. But empty elements has, remember, empty sets has no elements. And that is why we have nothing to prove. And we do not have any counter example. And we say it that this statement is vacuously true. Now, what do we mean by vacuously true? Vacuously true means that the statement is said to be vacuously true if it is considered true simply because there are no other cases which could falsify this statement. So we really do not have anything to check. So the condition cannot be violated. We call it as vacuously true. I will give you an example. For example, it's a very hypothetical example. Say, for example, we make a statement like all unicorns have wings. And there are no unicorns in reality. So there is no counter example to show or prove that unicorn have something without wings. And hence we say that this makes the statement what is called vacuously true. Because we don't have anything, so we have to say that this statement is vacuously true. In case of logic or logical propositions, I would say this type of examples are being used. So a statement of the form for all x in set A, some property holds, is vacuously true. Why? Because if set A is empty, because there is no way to disprove it. We move to the last and the most important part of today's video, that is what is a convergence series and what is a divergence series. Now first let us understand in a simple language what is a series. So simply it is a sequence of numbers, for example 1, 2, 3, 4 or A1, A2, A3, A4 and so on. And the corresponding series is S equals to A1 plus A2 plus A3 plus A4, and it goes on and on. And in order to make it in mathematical terms, we write something as this. S equals to sigma, the lower limit is n equals to 1 to infinity an, where basically an is nothing but these summation, A1 plus A2 plus A3 plus A4. Just that's it. So we get two types of series. One is a finite series. For example, 1 plus 2 plus 3, it ends at 15. So it is a finite series of fixed numbers. Another is the infinite series which goes on and on indefinitely. And from here we get two concepts, which is a convergence series and what is a divergence series. So first we will look in what is a convergence series. This is a mathematical definition. Go through it and then I will make you understand the simple point of it. A convergence series is basically an infinite series whose sum approaches a finite number as more terms are added. So mathematically, a series is convergent if the sequence of partial terms are this, which has got a finite limit n tending towards infinity, meaning this one. Okay. So let us understand in this way that a series is what we get when we add up numbers in a sequence. For example, any number, and then the series goes on and on and on and on. It is mathematically denoted by this sign. Don't worry, I will explain each of these, what the sigma and etc. means. First, let us understand the first important term, that what is a partial sum. We called it that approaches finite number and it is a sequence of partial sums. So let us understand what is basically partial sum. Partial sum is nothing but it is the sum of the first n terms of the series. So for example, if you consider the series this one, 1 plus 1 half plus 1/4 plus 1/8 and so on, then the partial sums are s equals to 1, s equals to 1 half, s equals to 1 half plus 1/4, s equals to 1 half plus 1/4 plus 1/8 and on and on and on. So the first few partial sums which goes on adding, this is what is called a partial sum. Now you have noted one thing, that it is going towards 1.75, 1.875. What does that mean? That means this entire series is slowly and slowly and slowly converging to 2. But there are certain implications which I will explain. So this series is converging and approaching towards 2, and we say it that limit of n approaching towards infinity as Sn equals to S. That means the limit will go on. So this 1/2, 1/4, 1/8, and it will go on and on. So that is why n is tending towards infinity. But the sum will become finite, which is 2. So that is why we call it converging at a point at some finite number. It can be 2, 4, 10, anything. Now, so this is the partial sum. Now, why partial sums are important? Obviously, it is important because if the partial sums are approach a finite number as n tend towards infinity, that means the series converges. And if the partial sums actually grows or becomes larger, which we will see, and oscillates, what do we mean by oscillating? I will come to that. The series diverges. So what is the meaning of this one? Limit n tending towards infinity and Sn equals to n, which is some number. Let us make a very simple example of that. So what it means is that if we keep on adding and adding and adding more terms, the sum gets closer and closer and closer to a particular value s, and we call that the series converges towards s. And mathematically we just like this. So nothing adds itself. For example, let us consider this geometric series. Okay, the partial sums are what? Say for example s1 equals to 1. So again n becomes 1. s2 equals to 1 plus 1/2. So n becomes equals to 2. S3 becomes 1.75, n becomes 3, and so on. And here you can see it is approaching 1.9375. So what happens over here is that you can see that n from 1 to 2 to 3, 4, 5, I mean to say the counting, the numbers that we are adding, this is the number of terms we take. And n is tending towards infinity because this adding will continuously go on. However, Sn will come and converge at a point which is 2. So this is what it is. So here you can see that 1.875, 1.9375. So it is slowly and slowly going. And it is actually trying to reach to converge to 2. Now, apart from this converging, apart from the limit that n is going towards infinity, one thing is very important. And the important thing is this, that remember that a convergence series actually never reaches its limit. Right, but it gets arbitrarily close to it. That means if we actually get something like this, say for example, if the sum gets increasing and the amount added each time gets smaller and smaller. So after one term s1 equals to 1, after 2 terms s1 equals to 1.5, after 3 terms it becomes 1.75, after 4 terms it becomes 1.875. After finite terms, what we see that it never actually reaches 2 in a finite number of steps. I would say in a number of steps. So what is the key concept? The key concept is that here you can see the series converges to 2, meaning that the sum gets closer and closer to 2 as n approaches towards infinity. So the difference actually becomes infinitely small and infinitesimally small. And the sequence gets arbitrarily close to 2, but it never actually reaches to 2. Now, as mathematics always deals with some weird and abstract concept, let us understand in this way what happens. Say, for example, that it actually reaches 2. What will happen? A hypothetical case. So there are 2 things which might happen. First thing is that if the sum actually reaches 2, we should say that the series is not infinite. That means it's simply a finite sum which say Sn equals to 2 or 3 or so. So obviously that means there are no need for limits because the sums are actually equal to 2 after a certain number of adding the terms. The second thing which becomes is that you see this series 1 plus 2 plus 3 plus 4 and so on. This is impossible for a truly infinite series because an infinite series is defined as a process that keeps adding terms indefinitely. So if something is indefinite, then how can it becomes a finite series? So if an infinite series somehow actually reaches 2, which we were thinking hypothetically at some point, that would mean that the terms stop contributing anything beyond that, which contradicts to our term of defining an infinite series. So it is never going to happen, and if it happens, it is not what we are trying to understand, convergent series. Now, when we say that it is getting close, but it will never reach to 2, That means, can we say that this concept is close to what we call asymptote? Now first let us understand what is an asymptote. So an asymptote is a function, a line that a function approaches, but it never actually touches or crosses in most cases. So if I take this, then what happens is that we can think the horizontal y equals to 2 as an asymptote for the sequence, and it will look like this. This is not with 2. I've just taken an arbitrarily simple graph to make you understand. So as an asymptote for the sequence of partial sum, Sn converges to 2 and n goes towards infinity. So next question obviously arises, that is every convergent series related to the concept of an asymptote? Yes, in a way. When a series converges to a finite value s for the sum Sn, it behaves like a function that has got a horizontal asymptote at s. But remember that it won't be right to tell, because series have asymptotes in strict sense. This is something which we are dealing with discrete mathematics, and the term asymptote is actually used in continuous function. So it won't be correct to tell that it is an asymptote, because the term asymptote is used in continuous function, and the concept of series, divergent, convergent, etc. deals with what is called discrete mathematics. So done with convergent series, we come to the next and the most important part, is that what is actually a divergent series. So is it just the opposite? Let us find out. So a divergent series, remember, it is it is an infinite series, but it does not converge in a finite number. In other words, what we can say, that as you keep on adding more terms, it happens two ways. One, it either grows infinitely large, or two, it oscillates without setting a single value. Sometimes this, sometimes that, sometimes this, sometimes that. It's a kind of a pendulum which oscillates here and there. Mathematically we tell as this. I will just make you understand about this. So what we can say is that does not approach a finite limit. As an approach towards infinity, this series become what is called a divergent series. An example, for example, this divergent series, harmonic series. This is what we call a divergent series. So either it will grow infinitely large, or it will oscillate it. N will become tending towards infinity, but somehow it will not converge, it will diverge. Question is that why does it diverge? And that's it what we are going to explore, taking the same harmonic series in the next part. So we take this part, the term gets smaller, which terms 1 upon n, but the sum keeps on increasing and increasing and increasing indefinitely. So if you keep on adding the terms, the total sum grows without bound. Now without bound is again a technical term which I will explain later, and it will never settle to a finite number. Mathematically we say this, sigma n equals to 1 to infinity, 1 upon n equals to infinity. This means actually that the series diverges to infinity. Now let us take an example and see what we are trying to make. So suppose we add few terms, s1 equals to 1, s1 equals to 1 plus 1 half. So here you see the circled one, the sum is decreasing, and 1.5. Okay, next 1 upon 3, and the sum goes close to 1.833. Then 1 upon 4. So here you can see the terms get smaller, but the term on the right hand side of the equation, it is increasing. 1.5, 1.833, 2.083, then 2.93, then 5.18, then 7.48, and on and on and on and on. So this is what we're trying to make, that even though each new term is getting smaller, that is 1 half, 1/3, 1/4, the total sum is constantly increasing and increasing without stopping. Hence we say this is a divergent series. It's very simple. Okay. Now let us take this same harmonic series and let us try to understand this mathematical term. What do we mean? So n, first of all, this big sigma is the summation symbol. We are adding terms. N equals to 1 on the top, infinity means it starts at 1 and goes to infinity. 1 upon n, what does it mean? It means that each term in the series of the fraction 1 upon n, which gets smaller and smaller and smaller as n increases. And this one simply means that even though the terms get smaller, the sum keeps increasing without bound. So here you can see that 1, 1/2, etc. So we say these sums never settle to finite number. Instead, they increase indefinitely. So we are done with the indefinite term. It increases 2.023, 5.18 and 7.48 and so on. Now the definition also says this part, oscillates without settling to a single value. What does it mean? Simple. Oscillate means in a series the partial sums keep switching between different values without settling to a single number, and this means that again the series does not approach a finite limit, it diverges. For example, if you take an alternating series, 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. So here you can see S1 becomes 1, then 0, again 1, then 0, again 1 and so on and so forth. So here it is 0 and 1, again it is 0 and 1. So it is oscillating, even, isn't it? It is oscillating. So since the limit does not exist, the series diverges due to oscillation. And the sequence of the sum is 1, 0, 1, 0, 1, 0 and so on. There are many other mathematics, there are many other terms and many other problems in divergence series which I will cover later. But in this series I just aim to make you an understanding of the basic concept of divergence and convergence series. So what are the key differences or relation between divergent and convergent? Let us understand in tabular structure. Definition is that a series approaches a finite limit as the terms increases, and here it either grows indefinitely or oscillates without a finite limit. Mathematical convergence, obviously it approaches a finite number as n approaches towards infinity, and it does not approach a finite number as n approaches towards infinity. Example is this one, and example is this one which we have seen. The graph behavior, if I take the sum levels of, here the sum keeps on increasing or oscillates indefinitely. If I take the key property, the sum infinitely, sums of infinitely, many terms are infinite and it never settles. And real world examples are Zeno's paradox, Achilles catching up the tortoise, a person keeps borrowing money without repaying, which is called a bankruptcy example. And importance is mathematics, yes, because convergence series is used in Foggy analysis, probability analysis, and divergence series is used in chaos theory, finance and physics. Now, Zeno of Elea was a Greek philosopher and mathematician from Elea, which was an ancient city in Italy, and he was a student of Parmenides, also known for his paradoxes, which challenges for understanding of motion, time, infinity, etc. Now, we will take one of his paradox, which is called the Achilles and the Tortoise race. And Zeno's paradox becomes very much important not only in convergence series, but it is actually important in terms of philosophy also. So what it says is that Greek philosopher Zeno argued that the motion is an illusion. Okay, and one of his most paradoxes is this one, Achilles and Tortoise. And you know Achilles was a great hero. He was invincible, except that you can strike his heel and only when he will die. So suppose this great warrior Achilles races against a tortoise, and given the tortoise is a head start. So you can see that right at this point that Achilles is over here and the tortoise is over here. Okay, Achilles moves somewhere here, the tortoise approaches here. So what it tells actually is that by the time Achilles reaches the tortoise starting point again here, the tortoise has moved slightly ahead. And by the time Achilles reaches the new position over here, the tortoise again has moved a little bit further, and so on and so on. So what it tells is that if this reasoning continues infinitely, Achilles will never catch up the tortoise, even though the common sense tells us that he will. So this paradox suggests that motion consists of infinite number of steps. Actually, it contains of infinite number of steps, making it impossible to complete. Do let me know that is Zeno's paradox finally has been completed, has been sorted, or it has been solved, or is it that motion to your idea, or what do you think, is still infinite, and do we still think or ascertain or continue with Zeno's paradox that Achilles, will he never achieve to reach the tortoise, or he will? Let me know in the comment box. So that is all for today's video. Thank you very much for watching this video. So if you have liked the video, please do not forget to subscribe to my channel Physics for Students and click on the bell icon so that you get all the notification from Physics for Students. And do subscribe to my other channel, General Relativity Explained, where now I am putting up videos related to general theory of relativity. And stay tuned to this channel Physics for Students, because in the month of April there are few important podcasts which is coming up both on this channel as well as my on other channel. So see you soon with more interesting videos and podcasts, but up till then, may the good Lord be with you.